Hi everyone. Welcome back to Dave's Math Channel. I'm your host David Tear, where this is going to be my second video on my sub-series on Gaussian primes of my series on algebraic number theory. So let's begin. So this one's going to be kind of short and sweet, by the way. I just want to prove this theorem. This is a very important theorem, actually. This theorem 2. It's going to tell us basically how to classify all Gaussian primes. So what this theorem says is that a Gaussian integer is a Gaussian prime if and only if its norm is 2, or a prime of the form 4n plus 1. In other words, a prime that's congruent to 1 modulo 4, or it's a associate of ordinary prime Q. I'm calling it Q here to distinguish it from P. So Q is just an ordinary prime now congruent to 3 modulo 4, i.e. the form 4m plus 3, and use a unit. So I think I forgot to say that. Q has to be a prime of the form 4m plus 3. So that's what we want to prove. Yeah, I think I did say that at the end. Yeah. So anyway, so we need some lemmas to prove this theorem, and they're actually pretty simple lemmas. So let's just do this. So our first lemma says that every Gaussian integer of a prime norm has to be a Gaussian prime. Well, this is actually very easy to prove because remember what I said earlier about norm being multiplicative? I mean, if we have a Gaussian integer whose norm is a prime, well, I'm calling it pi here. And this is the usual convention I'm going to use. I'm going to say pi is a Gaussian prime. Don't confuse it with the pi you learned in grade school, 3.14 approximately. It's not that pi. So pi here represents a Gaussian prime of norm P, where P is a prime of the form 4m plus 1. And since its norm is prime, let's try to factor this Gaussian prime pi, or Gaussian integer. We don't know it's prime yet. So let's just assume we have a factorization of pi as alpha times beta. So pi equals alpha times beta. That means the norm of pi is the norm of alpha times beta, but since the norm is multiplicative, that means it's the norm of alpha times the norm of beta. But remember also that norm is always a positive integer. So we have two positive integers whose product is p, and since p is an ordinary prime, that means one of them has to be 1 and the other has to be p. That's just a definition of an ordinary prime. So, I mean, without loss of generality, we can say alpha has norm 1. That means alpha is a unit, and that means beta is just going to be an associate of pi. So that's the proof. Remember, that's the definition of a Gaussian prime. A Gaussian prime is a Gaussian integer whose the only factorizations of which involve the product of a unit times associate. We place 1 in the case of ordinary prime with a Gaussian unit, which is just 4 plus or minus 1 and plus or minus I. Those are the only Gaussian integers of norm 1. We call those units. And the other one is what we call an associate of what we started with. It just means it's basically the same thing we started with, just multiplied by a unit, the inverse of the other unit. So I think you get the idea. It is a Gaussian prime. We've proved that. So, and there's an immediate corollary we can make. Let's consider the case p equals 2. I mean, yeah, so for this lemma, we didn't actually assume that p was congruent to 1 mod 4. I think I made a mistake when I stated this lemma, lemma 2.1. P just has to be a prime. So in particular, p can be 2. Well, what can we say about Gaussian primes of norm 2? We know they have to be Gaussian primes because 2 is a prime. Well, it turns out there's exactly 4 such Gaussian integers. They're all Gaussian primes. 1 plus I, 1 minus I, minus 1 plus I, and minus 1 minus I. If you like, they're the 4 Gaussian integers which lie on a circle on the complex plane of radius square root of 2. If you look at a picture of the complex plane, I think you'll see that there's exactly 4 of those. And I just said what they are. So anyway, yeah, that takes care of the case where the norm is 2. And then the second lemma, now we do assume that p is a prime of the form 4m plus 1. And if that's the case, then it turns out that any Gaussian integer of norm p has to be a Gaussian prime. And as a matter of fact, there exists such a Gaussian prime. For every prime p of this form, there exists a Gaussian prime of norm p. Well, we already proved yesterday, I think it was lemma 1.4, that there does exist a Gaussian integer of norm p when p is a prime of this form. And by lemma, the previous lemma we just proved, we know that since p is prime, that pi, this Gaussian integer, has to also be a Gaussian prime. So we're done. That was very easy to prove. So we kind of know what all the Gaussian primes are of norm p, where p is a prime congruent to 1 modulo 4. We even know how to find them. We can just use the Euclidean algorithm to find them. We take the GCD of p and k plus I, where k is a square root of -1. K is an integer such that k squared is congruent to -1 modulo p. I showed you how to find k last time. So we even know how to find them all. Anyway, and then the third lemma, now let's assume that q is a prime of the form 4m plus 3. So this is the other kind of prime. This will take care of all the primes. So every prime is either equal to 2 or it's odd, which means it has to be either congruent to 1 or 3 modulo 4. We already looked at the case where it's congruent to 1 modulo 4. Now we're going to consider the remaining case, the last remaining case, where it's congruent to 3 modulo 4. Well, in that case, it turns out there's no Gaussian integers of this form. And it doesn't even have to be a prime, it turns out. There's no Gaussian integers whose norm is of the form 4m plus 3. The norm can never be congruent to 3 modulo 4 for any Gaussian integer. So q didn't even have to be a prime. But we only care about Gaussian primes for our purposes. I guess that's why I made q a prime here. But it doesn't even have to be a prime. And this is actually very easy to prove. Let's assume that there is, I'm going to argue by contradiction now. So we're going to assume that there does exist a Gaussian integer. I'm calling it pi here. It doesn't have to be pi, but it could just be an arbitrary Gaussian integer. Since we can write it as a plus bi, we can always write a Gaussian integer that way, where a and b are ordinary integers. We can look at this norm, and we already assume that its norm is q, and we can write it as a squared plus b squared. So now we have a number q. It doesn't even have to be a prime, but here we are assuming it's a prime. So just imagine q is any integer that's of the form 4m plus 3, any integer that's congruent to 3 modulo 4. And we're claiming that that integer is the sum of two squares. Well, now we're going to prove that that's impossible. And why is that impossible? Well, it's actually pretty easy to see. Consider the squares modulo 4. So there's two cases. Either let's just consider one of these integers, a. So a is either even or odd. And if a is even, its square is divisible by 4, which means a squared is congruent to 0 modulo 4. Similarly, if a is odd, then it turns out that a squared is congruent to 1 modulo 4. Square of every odd number is always congruent to 1 modulo 4. There's no squares that are congruent to 3 modulo 4. I think that's pretty easy to see. Pretty easy to prove anyway. I didn't write out the algebraic proof, but I'm pretty sure you guys can do it yourself. It's actually pretty easy. So anyway, squares can never be congruent to 3 modulo 4. But what about the sum of two squares? Well, we just said that squares are always either congruent to 0 or 1 modulo 4. They can't be congruent to 2 modulo 4 either. So consider all the possible cases of the sum. If both a squared and b squared are congruent to 0 mod 4, the sum is congruent to 0 mod 4. If one of them is congruent to 1 modulo 4 and the other 0 modulo 4, the sum is congruent to 1 modulo 4. But they're the only remaining cases where they're both congruent to 1 modulo 4, in which case the sum is congruent to 2 modulo 4. But it can never be congruent to 3 modulo 4. I think that's pretty easy to see. So that's a contradiction. So we just proved that no number congruent to 3 modulo 4 can be written as the sum of two squares. That's actually a result about integers. It's not even a result about Gaussian primes. But it also proves that there's no Gaussian primes whose norm is a prime of the form 4m plus 3. That's a consequence. It's a corollary. And that's the proof of lemma 2.3. So now we're almost done. We just need one more lemma. And the one remaining lemma, still want to know what kind of what other kinds of Gaussian primes there are. Well, it turns out there's only one other type of Gaussian prime. We know that every Gaussian prime, every Gaussian integer whose norm is 2 or a prime of the form 4m plus 1 is a Gaussian prime. But it turns out there's another type of Gaussian prime, namely uh, uh, ordinary primes of the form 4m plus 3. Q equals 4m plus 3. Every prime like that, like 3, 7, 11, 19, so on. Those are all also Gaussian primes. And not only are they Gaussian primes, but all their associates are. We know that the associate of any Gaussian prime is also a Gaussian prime. So that's not saying a whole lot. That just means, for instance, 3i minus 3 and minus 3i are also Gaussian primes because they're all associates of 3. So up to associates, there's only one Gaussian prime of every norm Q, where Q is a prime of form 4m plus 3. So that will complete all of our classifications of what types of Gaussian primes we can have. And how do we prove this? This one's not too hard to prove either. So let's again now I'm considering associates of Q. So remember, Q is our ordinary prime. Like Q could be 3 or 7 or 11, but U is a Gaussian unit, plus or minus 1 or plus or minus I. So we could be looking at things like 3i or minus 7i, so on. So now let's factor that thing. Let's call it alpha times beta, where alpha and beta are now Gaussian integers. We want to see what their norms can be. Well, the norm of the product, the norm of UQ, so the norm of Q is Q squared. I mean, that's pretty easy to see. The norm of any integer, any positive integer n, is n squared. Because n, remember, the norm is the thing times its complex conjugate. So, if n is an ordinary integer, its complex conjugate is also n. So the norm is going to be n times n, which is n squared. So that's not saying a whole lot. That means the norm of q in particular is q squared. But we also said that's equal to the norm of, what's the norm of u times q? Because multiplying by a unit doesn't affect its norm. Norm of units are 1. But we're also saying it's the norm of alpha times beta, which means it's the norm of alpha times the norm of beta. And what can the norm of alpha and the norm of beta be? Well, let's assume that alpha is the one with a smaller norm, or if they're equal, they're both equal to q. Well, neither of them can have norm q because we just proved in the previous lemma that no Gaussian integer can have a norm that's congruent to 3 modulo 4. And since q is congruent to 3 modulo 4, that means that it can't be equal to the norm of alpha or the norm of beta. That means that the norm of alpha, if that's a smaller one, has to be 1. That means that alpha has to be a unit. And it also means the norm of beta has to be q squared, which means that beta is an associate of uq. It's another unit times q. So that means that q was a Gaussian prime. So that completes our proof. So now we know every type of Gaussian prime there is. We know, yeah, we just finished proving the theorem because that's all the theorem was saying. We went through every possible type. They're either norm 2 or they're norm p, where p is congruent to 1 modulo 4, and we know how to find all of those. Or it's equal to a ordinary prime of the form 4m plus 3, or one of its associates. Those are all the possibilities for Gaussian primes. And there's just one more thing we're going to have to do. I'm not going to do it today. But it turns out that there's only two essentially different Gaussian primes of norm p, where p is a prime of form 4m plus 1. A plus bi and its conjugate, a minus bi, its complex conjugate. Turns out those are not associates of each other. So we have two Gaussian primes that aren't associates of each other, but all the associates of all of those, both of those two primes are also Gaussian primes of norm p. So that's a total of 8. Because remember, there's four units, so we can take either of these two Gaussian primes we're starting with. One of them is a plus bi, the other is a minus bi, and then we get things like b minus ai, minus a minus bi, and minus b plus ai. So those are going to be all the 4 associates of A plus BI. Similarly, we can find all the associates of A minus BI. And it turns out those are the only ones. I haven't proved this yet. We'll prove this next time. And that'll really complete our classification of Gaussian primes. And this is a very, very useful result. I mean, knowing what all the Gaussian primes look like, what their norms are, well, we kind of know how to find them. As long as we can start with an ordinary prime, and then we know what all the Gaussian primes are with that norm. And another very useful fact, I'm going to give you a little bit of a heads up. Another very useful fact about Gaussian integers, they're what are called a unique factorization domain. You guys are probably familiar with a fundamental theorem of arithmetic that says the ordinary integers are also a unique factorization domain. All that means is that every prime factorization is unique up to ordering of the factors. And I'm sure you guys all learned this in grade school. Maybe you didn't learn a proof, but it's true. I think I will prove that. And I'm also going to prove that the Gaussian integers is also unique factorization domain, which is a really nice result. And you'll see why it's nice. I mean, it'll allow us to basically determine all the possible ways in which you can represent any integer. It doesn't even have to be a prime, but any integer at all, any positive integer. We'll be able to find out all the representations of that integer as the sum of 2 squares, just using these facts. So we're almost there. We've almost gotten to the point where we can classify we can find all representations of the sum of every positive integer as a sum of 2 squares. And by the way, I just proved that you can't do it when n is congruent to 3 modulo 4. That's one case. There's other numbers you can't write as a sum of 2 squares either. But we'll get to that later. Anyway, that completes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time.